Hello, welcome to Lecture 9. Today's topic is testing. So, in the spirit of this course and our Agile approach, we've been covering a little bit of Scala, a little bit of Chisel, a little bit of design methodology. And this current loop going around, we're overdue for some more design methodology. So, in the last lecture, we covered how to take things like priority encoders and one-hot encodings to build up arbiters, and then in turn build up things like a crossbar. But testing is really important, and we haven't given that enough attention. And so that's what today's about testing. So, what are we going to do? Well, make the case for why testing is important. We're going to show examples of testing a combinational component. That is something that has no registers in it, and that's something much easier to test and get really strong confidence in our tests. We'll talk about how to organize our tests better, something called Scala tests, and then we'll talk about testing a stateful component. That is something that has registers in it. In this case, it has the couple interfaces. This is our good old friend, the trusty queue. Let's go ahead and fire up this notebook. So why are we testing? Number one, uh, who wants hardware but is not known to work, right? Yeah, not helpful, right? If you're going to spend time with this hardware, it better be known to work. Um, you also need to prove to yourself it works. That's an important step. You also, beyond proving to yourself, to also take this hardware, you need to prove to others it works, right? And so these tests aren't just the fact of making sure it's correct. You also want to be able to prove to people it's correct. That's an important step. But beyond those two things, uh, underappreciated, tests help you develop better hardware. Um, if you use tests not just at the end, but along the way, you will both develop not just more correct hardware, but be better designed for testing and have higher quality tests. Get testing as part of the process. That's what we're arguing for in today's lecture. Okay, so in this testing lecture, we're going to cover a few concrete skills, right? So, number one, what are the actual API functions, but more generally techniques we can use to do testing, and what abstractions can we build up to make testing more productive? And I really want you to kind of get sold on this, right? Testing isn't just something you do at the end of the detail. No, no, it's part of the process, and you do it well, it actually makes the process easier and smoother, right? The whole point of agile programming and this agile development has been to be more productive, make higher quality outputs, and getting testing as part of it, making it an integral part of it really helps with that, right? There's some cool tricks how to kind of take the best advantage of what's available in Scala, Chisel, and Chisel tests to kind of pull this all together. Um, so for testing, there's three main components, right? Um, First off, you need a test case, right? So, what is the actual thing being asked to do? Initially, you can write these by hand, but at some point, maybe you also might want to use some kind of code to actually generate these. And of course, when you generate these, you can generate every possible combination, which is possible for very few inputs. If you have a lot of inputs, maybe you need to do it random. Sometimes random is too random, and you want to do what's called directed random, kind of choose certain things to kind of steer it. Um, when you have these inputs, then of course the question is for a test, it's both give the input to the hardware module, and then the hardware module responds, and you kind of see, well, is that correct, right? So testing is the automated checking. And so the question is, well, what is the right answer? It also needs to be part of the test. For your very first version of a test, you can, once again, handwrite these, handwrite the inputs, handwrite the outputs. That can work to get started. But of course, this is brittle, right? We'd much rather have a more reliable way to do this. And so the methodology we use in this course is what we call model generated. We're going to write Scala, which is not Chisel, it's just pure Scala, that does functionality we care about. It'll model what the component's supposed to do functionally, and we'll use that to tell us what our answer to hardware should be, right? So we will give a input to both the chisel design under test as inside a test bench. We'll also give the input to the model. The model will, tell us what the output should be. We'll make sure that the chisel matches the model. Now, the right question would be, well, who checks the model, right? And that's up to you. So there's different ways to kind of check these models to make sure that's true. In this course, we're going to handle it a little bit and say, well, hopefully our models are simple enough and short enough we kind of can visually inspect them and hopefully really clear. But in practice, checking models is a really important thing. When it comes to things like the project, you may find certain scenarios where you can, for example, find functionality you're trying to build in your project in Python or Java, and then compare that to your model to make sure your model's correct from the beginning. And okay, so we have the input to our test case, we have the correct output, we're done, right? Actually, we need one more thing for testing, and that is a way to actually perform the test, right? And so you need some sort of way to instantiate the hardware, feed it the inputs, extract the outputs, and compare. And so there's a whole bunch of scripting execution involved with this, a lot of collateral. And so if you think about this in the common case, in the general case, you think, oh my gosh, how do I balance flexibility, portability, speed, etc. Uh, for this course, we can just kind of hand this down to you. So for actually simulating your design, under the hood, you don't know it, but there's something called Treadle. It's a Scala-based way to simulate chisel code. So great, simulation, check. Who is actually doing execution of these tests? Chisel tests, the thing I was telling you about, I was so excited about. And then how do we organize things under multiple tests and kind of pull things together? We're using Scala tests. So those are the three tools. Like I said, for this course, we've already made these choices. You don't need to worry about this. It's already solved, right? When you get code for a homework repository, it's already using all these things for you. It's already all configured. But just for curiosity, that's what's making it happen. Cool. Questions so far? Okay. So if you're making these tests, oh yes, go ahead. I do, okay, good question. The question is, how do you make sure your tests aren't too circular in the sense of like your model being the same as the thing you're testing? For really trivial components, your model will look a lot like the thing you're testing, and I think that's okay. I think you're right for testing robustness when possible. It's nice to have your model be written in a different approach than the actual module, a thing under test. So that way, just like some, orthogonality, some differences there. But sometimes it's inevitable. This is going to happen. Um, and I guess one thing I should also mention later on in this course, we also will cover formal verification. And with formal, you actually do want them to be the same, right? That's the whole point. And so um, this is more of this kind of, dynamic empirical testing rather than formal testing, right? Um, okay, so you're making tests. What should you be thinking about? Uh, as I've always said in this course, right? Close the loop. That's the course slogan, right? Get things going as soon as you can. So we want to get some test case running on something as soon as possible. We want to do test-driven development. Um, how can I get some simple test bench running on some simple version of a module as simple as possible? Um, then something comes up a lot. You might hear this term coverage in design, and coverage refers to what fraction of the hardware's functionality have you actually tested, right? You can write a test that does one thing, and your module may do five things, right? So that means you've not tested the entire module, you only tested 20% of its functionality, right? So you should be thinking about what do you actually want to make sure you cover your testing and make sure your testing actually covers all those functionalities. And then the third thing that comes up a lot is how should you think about your design? So I use the terms opaque and clear here. In other communities, you may hear the term black box or white box. Black box meaning, or I use that the stand in for opaque. In other words, you can't see inside the module. So you know what the module is supposed to do functionally, but you have no idea what's going on inside of it. The alternative, of course, is white box testing, where you know exactly how it's implemented. And so it's kind of trade-offs for both, right? The advantage of black box testing, for example, as suggested earlier, was that way, if I don't know what's written inside there, I can kind of forced to be more defensive. I'm forced to kind of really make sure everything works correctly. However, if I'm doing white box testing or clear testing, I can see inside there. I can know where the corner cases are because I can read the code and see the code's corner cases, make sure I'm actually hitting them. And so, what do I recommend? Both. I think you should make sure you cover the cases users will see, which is kind of that opaque case from the outside. But also, you know yourself, right? You put in some special case inside the hardware. Make sure you have those edge cases actually tested and you actually have that coverage. Okay, so then uh, when are we actually testing? As I've been saying all lecture, imbibe it, embrace it. It's going to be integral, right? So it's not just the end final verification. When you're first developing, as I said, you want to find the simplest test bench, simplest module, and get them running together right away. So you're using that for to get things going. As you start getting going in the module and get more and more sophisticated, you use something called continuous integration, which means the tests are going to be running on your module in the background. It's not you running it manually all the time, but things like your GitHub server can run it for you in the background. We'll come back to that material later on this quarter, but just be aware it's another time this comes up. One of the most important times of testing is actually when you're talking with external collaborators, right? Because someone puts a pull request for your code on GitHub. If it's a one-line fix, you can look at it and be like, I can probably reason about that. Like you drop 100 lines on you. Did it break anything? I don't know. Well, how would you trust someone else's code inside your code? You'd want to audit it. You want to definitely look at it, but you also want to check it. So how do you check it? Tests, right? You're check it with tests. And better yet, if you share those tests publicly, the person contributing this can run those tests before they make the pull request, asking to send you the code so that you can know it's going to work in the first place. Another time you want to use tests is doing design space exploration, right? You have a parameterized hardware generator, and you want to tune those parameters to see, how it does in the design space. So in this case, you're actually using the test to animate the design. Hopefully it's correct, yes, but it's also a way to kind of see performance, for example. So there's a lot of different times you want it. And so like I said, it's really important to not just do testing at the end, but along the way. It makes the along the way process easier and better. But also by doing testing earlier, you actually can do testing better. And so, for example, you may find there's this massive, super complicated module. It's really hard to test. That can happen. How can you avoid that? If you include testing earlier in the process, you can design abstractions and even adjust your module boundaries to ease testing. For example, a module which has no state internally, it's just combinational logic, is so much easier to test. So if you can kind of decompose your design into things that are mostly combinational and things that are the stateful elements, you can make it so much easier to test. So, like I said, considering testing early is a great thing. It's often referred to as design for test, DFT. Usually the hardware folks use refer to making the chip design for testing the actual physical chip, but I'm using today to refer to design, actually changing the way you design so it's actually easier to test in the RTL world. Cool. Okay, so what's it look like inside Chisel? Uh, I've been extolling the virtue of the generators all quarter. Don't write a single design, write a generator. Are generators harder to test than single design? Yes, because now you need to test uh, multiple things. So what can you do? Well, what we recommend doing in this course is if you parameterize your test environment, someone can then use that to test an instance that came out of your generator, right? In other words, let's say your generator can produce n possible designs because you have that parameter can go from 0 to n. Uh, you don't want to write n test benches, right? You want to write one test bench is parameterizing that thing. And so then the user, when they can use it, they can then um, turn that test bench to that same parameter and it gets that same instance tested. So we aren't exhaustively making any kind of strong guarantee about every possible parameter combination being safe. We're giving someone the power by having this parameterized test to make sure the instance they're actually using is tested. Um, cool. What about chisel tests? I keep hyping it up. You've seen it all quarter kind of already. It's a way to write test benches directly in Scala. It runs what you write there in that snippet. It's a Scala program. It has that talking to a simulation of the design. For this course, we're using something called Treadle, which is, as I said, a Scala-based simulator. And so it's all in Scala land. It's all in JVM. It runs pretty fine. Treadle, of course, a simulator, eventually for massive, massive designs, is not the fastest thing in the world. But turns out for small designs, it has a very fast startup time and it's way easier to use. But there are ways to actually change the simulator you're using. And even when you change the simulator you're using, it's now running in a different process. It still talks to your chisel test bench, which is still a Scala program. So, for example, if you use something called Verilator, which will generate a custom C++ program for your hardware design, that will be one program running, and that simulation will be controlled by chisel test, which is a Scala program actually talking to it and exchanging data values and stimuli and that kind of stuff. Let's say you have a commercial simulator you want to use. That's also possible. Um, and so, yeah, um, these are situations for this course. Trust me, Treadle's fine. You can have millions of cycles of simulation there. You can generate waveforms. You'll be happy. You'll be fine. But yes, there are, of course, other tools. So I promised you combinational components were easy to test. Let's talk about it. So combinational means it's stateless. That means no matter whatever I do, if I put the same inputs in, I'm always going to get the same outputs. A stateful element, I can give the same inputs and I may get different outputs because it may depend on the history of prior inputs, right? So if I'm testing a combinational component, of course, you should be thinking about, how much range do the inputs have? What are the range of parameters? And then how do the parameters impact the size of the input space, right? So if the combination of all these things together is that the space of possibilities is reasonably small, I can just test things exhaustively, right? That's high confidence, right? I tested every possible scenario and that works. And so sometimes you can do exhaust testing. That's great. Um, However, you can imagine that if the parameters get made too big, that search space gets way too big, and then exhaust testing is not an option. So let's see how that play out. So let's imagine we're building an adder for a sign and magnitude numbers. So remember, sign and magnitude numbers, we have this notion of there's the magnitude, or mag n, which is a uint, right? And the sign tells us if it's positive or negative, right? And so if we want to do an addition for this, well, if the two numbers have the same sign, we simply just, copy the sign to the output and add the magnitudes. However, if they have different magnitudes, adding a positive to negative or negative to a positive, we need to subtract the magnitudes and then set the signs accordingly. Cool. Um, Great. So then let's write a test. Like I said, we wrote that module. Let's write a test right away. Our first test, what do? Well, I'm going to set uh, +4, so the sign bit is false, and it's or +1, sorry, and I think +2, and then I'm going to expect 3. So this is all handwritten, so to speak, and it runs through. And as we've seen before, if test bench works, it actually tells us nothing because it's supposed to work. But let's say expected 4, it's going to break. I got 3, was expecting 4. Okay, so great. 1 plus 2 is 3. Thing is working so far, but we've tested exactly one input case here, right? And that was a lot of work to write. So I can make this more efficient. As I said before, let's build a model. And so to the point of, well, gee, if I'm building an adder, at the end of the day, aren't I just going to be doing a sum? Yes, you are. However, you can see there's more lines to this than just the sum. So what the heck is all this other crap? Well, I'm representing the truncating addition, right? So if we go back to our design, which, it's important to think about what properties we were designing for, we have a W bit input and a W bit output. So as a result, truncation is possible. Meanwhile, a Scala int is 32 bits. So first of all, someone wants to do a W way bigger than 32. That's not going to work because we can't represent that with a Scala int. There is a big int class, which of course can be arbitrary, but not using that right now. But also we want to model the truncation behavior. So to model the truncation behavior, uh, we kind of have this binary arithmetic, which I'm not going to go into right now, which computes a mask and does some cleverness to apply the mask, and it works out. Part of the complexity here is that this is a signed number, and so to handle a signed number, you have to do some extra stuff. But say, for example, I, have a 4-bit W and add a, A and B. 4 plus 4 is, 8, 9, etc. Now, like I said, so 4 plus 4 being 8, that fits fine in 4 bits. Uh, if you made this 3 bits, for example, 0, right? Because you can't fit 8 in 3 bits. If I made this a little bit smaller, it's 7, it does fit. So this model is reproducing the truncation behavior. But big picture is this model, given A and B in the width, reproduces the number, it has some constraints on the width. Okay, so now we have a model. Are we done? Not quite. We want to kind of automate more things, right? Make tools do the work. So here we have this function, which is going to take in 2 numbers to test, a unit to test with, right? This module right here. And then what's it going to do? It's going to, of course, set the test, right? It's going to poke in the inputs into the module under test, right? The C. And you see, for example, for the sign bit, for example, it's setting that based on the numerical value of it. And then for the magnitude, it just calls into our model to do the addition. And then for the sign bit, it also calls into the model and it checks less than 0. So yeah, let's say we want to do 2 plus 3, no problem. So you can see how this kind of all fits together. So I've added some print statements to kind of make this all print out pretty, but yeah, 2 plus 3 went in, the alpha was 5. We can see the test bench passed with no issues. So this test bench is kind of concise, right? We have the ability to kind of have a parameterized model. We have this test add function, which kind of wires things together for us. That's kind of that third bullet point of, how do you kind of automate the interaction, and can do all that stuff. And now writing a new test bench rather than writing 6 lines like we did a couple slides ago, and having to set the inputs manually in the output. Now writing a new test case is easy as just writing 1 line. And notice how not only am I just writing the two inputs, I actually don't even need to write the output because we're using the model to compute the output for us. So we're actually just set more automation, less chances to get this wrong. Okay, now let's come back to this comment. Uh, I have this comment here about the sign. And so what's going on with the sign? So this is both visible in the code here and just a general issue with sign and magnitude. Maybe folks remember back to undergrad. What's the challenge with sign and magnitude numbers? Or I'll give you a hint. Uh, why why do I have this if statement? Why can't I always just trust the output? As a third hint, I'll say look at the text output for the test cases and see if anything there looks a little funny to you. Yeah, yeah. So it's one of these things. Mathematician is zero, positive, or negative, and kind of ask you like, yeah, as you said, like that doesn't make sense. But with the encodings, we can have positive and negative zero. So you can see down here, we have negative zero, right? That's a known when you use the sign and magnitude numbers. This is part of why it seems like two's complement are great because two's complement only has 1 0. So if you ever worked with floating point does have 2 zeros. There's a positive, negative zero, which most people seem like a bad thing, but actually, for things like representing limits, actually having both zeros is considered a feature. And so in this case, we kind of put a hole in our test bench because, yeah, wait, there's some funniness about zeros and signs. And so, yeah, if it's not zero, use this comparison. If it is zero, this effectively is not checking the sign bit because there's no specified behavior, right? We just specify when we get the result of zero, should be positive or negative. We have no model for that, and so we're just not checking the sign bit in that case. Small detail, but it's kind of interesting. But big picture, yeah, this complicated function is doing a lot of work for us, and now we can write tests as simple as just writing a new test, right? Like two inputs, and it talks to the model, it sets up the inputs, it checks the outputs, it even has some print statements in there for us. Pretty cool. These print statements, of course, are also gated by a verbosity flag, which by default is true. That's why we're seeing it right here. But as you can guess in a minute, we're going to turn that off. Um, so what if I just want to try every possible combination? So given a input, I'm going to now pick the maximum value and then try all maximum values for A from negative to positive, all positive from B, and there we go. So exhaustive testing for 2, not too bad. I forgot what the cutoff for this laptop is, so it'll be kind of fun to find out. I think it probably can do 4. Oh yeah, it's not breaking a sweat yet. Remember that whatever this number is, right? Let's say 4 bits, right? Well, it's one input's 4 bits, so two inputs is 8 bits. Um, and so yeah, so uh, 256, that's not too bad. But you can imagine as I crank this up, it might start to get slower. Yeah, took a little bit of time. And we'll keep going until you get bored, right? It's taking longer. And yeah, I think maybe 8's about as much patience as I have for today. 4 things working. Okay, still passing. Exhaustive testing, it's working. So you can see in this case, right, having this abstraction built in the prior slide, test add, we can easily just chuck in more inputs at it and, go to town. And also by turning off the print statements, our screen's not full of, gibberish, right? One thing I want to emphasize about tests, right? Tests aren't just the fact you ran your design with some sort of input stimulus. The test is also checking the output for you, right? If your response is, I want to, you know, scroll to line 5, read the output. If this line 5 is the value 6, that means it works. That's not a test. That's debugging with printfs. That's not a test. The test needs to automatically check for you. Is it correct or not? Okay, cool. So that was exhaustive testing, which, as you saw, eventually it's going to run out of steam. So what's the alternative? The alternative could be, what if we did it randomly, right? So we just say, hey, you call this function, and I'm going to randomly generate an input and just have two inputs randomly generated and then test it. So yeah, so we can pick some number of trials and just let it run. In this case, I'm leaving the verbosity on so you can see what it's trying. So yeah, randomly generated 5 test cases for us. No problem. I can run this again. It's going to generate 5 new test cases. So you can see already we've built our way up, right? Even though it's something as simple as an adder, we had the ability to kind of exhaustively test all inputs, which makes sense if W is small. As W gets bigger, that's maybe not a good idea. We can do things like random testing, etc. So you can see we're kind of building up abstractions. Rather than just writing simple test cases, rather than doing tons of copy pasting, we're writing code to kind of build up something more sophisticated about this. Cool. Questions on that? Great. Okay. So let's organize things. So Scala tests we've been using under the hood, not really necessarily knowing it. Like its name would imply, it's descended from Java tests, right? So everybody's going back to Java. So the SBT tool we use in this course for things like the homeworks is aware of Scala tests. It knows how to talk to it. So for example, if you say test, it knows how to go digging into um, the source repo and running the tests. You also can say, hey, I only want to run a certain test. Great. Chisel tests internally depends on Scala tests. So these Scala test features does also work with chisel tests, which is great. So you've already been using this and didn't even know it. Um, so, uh, for example, uh, with Scala test, you can actually not just write a test case, you can write a test case that actually um, appears. You remember in the homeworks, when you run things, you kind of see this green text when it's running, right? So the green text is coming from the tester. The black text is coming from our test bench. Our test bench has that printf inside there, right? Um, and so let's kind of compare this for a second, right? So here you can see we have this sign mag test. What is this stuff over here? This is the boilerplate for the testers, right? This any flat spec comes from the Scala test. This comes from Chisel test. Um, and then the internal structure here is how I actually make these test cases so that it appears like this over here. For example, behavior of is this block of tests. So this is, sign mag add. You can see already I'm kind of doing string interpolation to fill in the bit width for us. If I change the bit width, it's gonna, change the output here, which is kind of nice. Um, and then we actually have the label for the test. So here I actually chose to just write out what it's doing. Maybe you'd use English words to describe it. Now, the syntax, if you're looking at this, might look a little bit silly, right? You're like, wait a second. Behavior of, there's like no dots in here, there's no parentheses, what's going on? So in Scala, one of the features they designed this language for is to make it easy to develop new languages on top of it. So as part of that, in the language, uh, in most languages of object-oriented programming, it would be behavior dot of like this. So this should also work, and it does. But it turns out that the Scala parser is smart enough, the language rules allow it, that instead of requiring the arguments to be in parentheses, you can put them just separated by a space. And then you also can replace the function name with instead of a dot in there, you can actually have a space, and it's going to figure it out. So really, yeah, you are calling a function there. And the reason why designers of Scala test chose to do this is it kind of looks human readable, right? It says, oh yeah, behavior of blank, and then it should is these are keywords defined within Scala test. This is an argument. This is another function call. And so like I said, for now you kind of choose this boilerplate where basically you fill in what goes in the quotes, but you get these nice kind of tests you can kind of have appear inside your thing, etc. Cool. Questions? Okay. So we've seen sometimes a lot of lines of code dedicated to poking wires. And if you put those pokes inside of a test bench as an automated function, it's not so bad. But sometimes you still want more conciseness. So there's a feature called bundle literals, where there's a way for you to instantiate a bundle full of constants or literals and then connect that together. So here I'm doing that to generate B0 and B1 and even S. So you can see in this case, I'm doing 2 plus 2 to get 4. And I'm showing different ways of declaring it. This is a feature which is still, I believe, in experimental chisel, still not been fully blessed. Um, but yeah, it lets you describe that. And yeah, you can see one way to write it is like you say the bundle type you want, dot lit, and you fill it in. Another style, which I showed on this thing, is you actually can also use reflection to identify, sorry, not reflection, introspection, apologies, to identify the type of the thing you're working on, and that way make sure the types match up. So in some ways, this is more robust because this is saying, okay, what type is here? Let's grab that, and then we can go ahead and populate it. But at the end of the day, this is still going to just, plug in literals and test it. Usually it's interesting. Otherwise, don't worry. Question. Yeah, so remember, yeah, question is what's going on here? So here I'm setting the poke for N0 as B0. If I go back to our module, remember this is a sign and mag, which is a bundle which has two fields. So instead of having two pokes per input, I'm having one poke per input now. And it's a small win. Like I said, this is something I find this syntax so verbose and scary. I don't usually bother with this, but maybe you find that better somehow. Cool. Okay. So for a finale, we're going to take Chisel, which has a Q class, which we've already seen in the prior lecture, and we're going to build a way better tester for it. So in the prior lecture, I kind of had this very manual thing that was kind of dicey. We're going to build a way better tester for it. So why is this interesting or challenging? And then make sure you have time for this, and we do. Queues have state, right? They have registers or even SRAM to hold what's going on inside there. And so how are we going to go about testing this in a way that makes sense? Number one is exhaustive testing is probably not going to be possible. Uh, the test that we're going to show today, I can't promise is like the perfect tester that guarantees Q is 100% perfect. But we are going to show is how do we make a model for a steeple component and plug it into a test bench around it to kind of build up abstractions. We just saw that a second ago with the sign and magnitude adder. We built up all these abstractions. So at the end of the day, we could simply just generate test cases in one line. We could do exhaustive randomly easily. We're going to do that kind of similar with the queue, but mostly just worry about how to build that infrastructure up. So remember when we had the chisel queue, oops, we have, a type, number of entries. We talked about these parameters, right? For example, pipe being true lets you have it in queue into a queue that's full if it's also dequeuing. Flow, we're going to leave false for today, which is the ability to kind of bypass the registers if it's empty. And remember, the inputs to queue and the outputs are all decoupled. Okay, so first we need a model, right? And like I said, the model gets tricky because we're trying to represent the behavior of registers. And so in terms of the queuing functionality itself, guess what? There's a queue in the Scala language. We're going to go ahead and use that. Notice we're using the mutable queue. So we're actually going to like do pushes and pops on this queue. It's going to change. That's not our immutable style we normally do, but you know what? We'll take that. So that's MQ or a mutable queue. Got it. But what does the model need to do? Remember, the queue has two sets of ports, right? There's the input ports and the output ports, the NQ and the DQ. And so both sides are decoupled. So that means we have ready, valid, and bits on both sides. So, for example, let's say someone asks the model, hey, is the DQ side valid right now? In other words, is there something that can come off of this queue? Well, that should be the case that the actual queue inside this model is not empty, right? Um, so yeah, you may have seen this before. I mentioned this a second ago that, Scala is very verbose. So rather than saying, not dot is empty, they also have it is empty and non-empty because why not? If that kind of stuff appeals to you, there is a link I have on the homepage under Scala references. There's a blog I linked to where someone has a lot of good idioms and, common mistakes about writing Scala. And this is true for any language. You can write code that is totally correct, but there's a way to do it more elegantly if you know that language better and kind of embrace it better. And so that guy has a blog kind of listing them all. I'm very optimistic in the modern era of all these large language models, LLMs. As you're writing the IDE can tell you, know what, is this better, code suggestions and that kind of stuff. And so here's an example of something that's kind of a little bit unintuitive, but maybe not, you wouldn't think to look for it, but it's kind of makes it nicer. Okay. Then what else do we have? Well, we have some more functions. For example, let's say attempt DQ. So what does that mean? So remember, the DQ happens if the DQ side, the output of the queue, is both ready and valid. So we make sure that's the case, right? So in other words, hey, um, if ready and valid, then yes, we take something off of the queue. And the Scala terminology for pop is .dq. Okay, so yeah, we wrap that into sum. Meanwhile, to be more elegant, take advantage of Scala, guess what? If someone tries to DQ and there's nothing to DQ, whether it be the queue is empty and it's not valid, or perhaps it wasn't ready in the first place, uh, we say, hey, none. It's an option type, right? And we're saying there's something coming out. And then this DQ ready, what is this? Remember, DQ ready, the ready port on the DQ on the outside is a input coming into the queue. So in the model, the way we represent that as a mutable field, right? That was a choice I made. Alternatively, you could have DQ ready be a parameter in a lot of functions, different ways to handle it. On the NQ side, what do we have? For example, is there room to NQ? Well, if I have, free entries, otherwise I'm less than num entries. So even though this Scala queue can grow indefinitely, we're parameterizing our model such that it caps number of entries to be less than that. Sure, great. However, let's say I'm already at the limit, but um, I'm going to DQ with that pipe thing we talked about before, also allowed. Cool, we modeled that behavior. And then if someone wants to do an NQ, right? If someone wants to do an NQ, they give me an element. Well, if I'm ready to NQ, great. I go ahead and append it to the queue. Um, and so, yeah, and so you see here in the comments, the fact someone's calling this function is kind of implying that the NQ valid is true. Whew. Okay, so we have a model. It works. There's some subtleties here, right? The biggest subtlety is that these registers internally, which in this case are actually that, MQ. Um, for conventional logic, it's really easy to map models like we did for the adder. For stateful elements, you gotta be careful because in programming languages, you can have a sequence of variables. Let's say they're all references, fine, or let's say they're mutable and you change them. But we kind of think of it still as a sequence of events. Remember, in hardware, of course, things are kind of simultaneous, right? So what we don't want to have happen is have somebody modify a register that will be changed at the end of the cycle and this one gets the wrong value too soon, right? Register is kind of the case where you change inputs to registers and then you don't get a new value until the next cycle, right? And so to kind of model that behavior, a best practice is to, if any register is internal to the model, make sure if they're ever going to be changed, for example, like MQ, that happens last. And if anyone's going to be reading those registers, it happens first. So that way you're okay. The alternative is for registers to actually have two copies, the copy you're allowed to read from and the copy you're allowed to write to. And then at the end of the cycle, your model will copy the right ones to the internal values. Two ways of doing it. Okay, we have a model. So with our model, here's some examples. Say I want to push one into it. Oops, I didn't load the prior slide. You can see, for example, yeah, I can go ahead and push a one on, no problem. I can push two and pop one. And so you see when we temp DQ, we get a value out. Yeah, it works. Once again, yeah, oh my gosh, there's so many fields to set to like mimic this, right? For developing this the first time, maybe manual is okay, but we want to automate this, right? So get bootstrapped, close the loop, get things going, and then let's build up. So what if we want to do the same thing, but maybe just run a little longer, some prints in there? Sure. We can see, for example, initially we're trying to NQ, and we don't let it DQ until after the first three cycles. So for three cycles, we NQ, and so we can see the DQ becomes valid after a cycle once originally it's empty, and then after one cycle we have something in there. And we see, for example, okay, sure, and then after three cycles we start turning on a DQ ready, which is here. And when a DQ ready is on, then of course things start coming off the other end. So I wrote some arbitrary scholars to try and get a longer test case running, but there's still a lot of work going on here. Um, so uh, this is just the model running. So let's say now I take an actual chisel queue and the model, and I want to make sure it's doing the right thing. So this long bit of code is only doing a few cycles, right? It's going to instantiate the model, and then it's kind of comparing the two, right? So it's doing a lot of specs in there, but it's also doing work to make sure the model is in sync. And so, for example, I'm trying to dequeue from empty and make sure it says it doesn't work, then an NQ1, and then NQ nothing and DQ1. So this works, right? You can trust me that it works, and that no errors popped up. Oh my gosh, this is a wall of text. What if one line was wrong? How would you know? Um, what can we do? Well, let's automate the interaction, right? So basically, for a given cycle, what are the key things we want to do? We basically want to see, are we trying to NQ? Are we trying to DQ? And if we are trying to NQ, what's the data? That's it. And really, the rest of stuff can take care of itself. And the reason why the rest of stuff can take itself is because we have a model to compare against, right? So we can see now in this function, this is kind of the key link. This function is going to use the model and make sure the actual chisel queue matches up with it. So you can see you kind of have all this cleverness to make sure it syncs up. So for example, from the input DQ ready, make sure the model does that. We also poke that into the actual chisel module. Um, we make sure, for example, that the DQ valid from the model matches the actual chisel component, etc. Um, this all kind of comes together. And so, yeah, now running a new test case per cycle is as simple as writing, one of these, right? So we're passing in design layer test, which is the chisel module. DUT is a classic hardware abbreviation for that. Our queue model, and then we're saying, hey, we're not going to enqueue anything. Or what if we are queuing something and it wants to be one? This works. Cool. Questions so far? Okay, but I wrote the print cases and there you can kind of see the queue is originally empty. Now it's one and it's empty. This is the key thing, right? The model as well as automating the interaction between the model and the design. Those are the key parts. Once you have those two things together, then you can write test cases so much more productively, like this. But let's say I want to write something spiffier, right? If I want to test filling it and then draining it. So now when I can write test cases so simply, I'm just going to fill up and then drain it. So we see, for example, yeah, it fills up, 3 entries, 0, 1, 2, 0, 1, 2. I can make this, 5. We'll see it actually runs longer. So it's the power and parameterization of both of the sizzle as well as the test bench. So yeah, we can now make sure it does the right thing. Maybe I want to, run it another cycle to really try to overflow it. That works. So that means it's going to eventually reject it. And because of the model telling us it should reject it, it's doing the right thing. So we're kind of building these kind of more sophisticated testing abstractions. What if I want to try and do it randomly, right? What if I want to just make up some numbers, right? So how are we doing this? Well, I'm going to use random to pick a Boolean for what I'm trying to enqueue and what I'm trying to dequeue. And then for the number I'm enqueuing, it'll just be whatever cycle we're on. Okay, let's run this. And we see, oh yeah, it happened to enqueue1 and then not do anything for a while and enqueue to 4. If I run this again, it grows. This time it grew and then it shrank, right? Because it randomly chose to enqueue or dequeue. So you can see once again, with the right automation in place, it becomes a lot easier to kind of keep writing more and more tests to kind of build this whole thing out. Cool. So wrapping up the lecture, what are the kind of key points? Key point number 1, get humans out of the loop, right? We're trying to do automated testing, right? You're writing these tests. The goal of rather than writing oodles and oodles of tests is instead build abstractions and code so it generates tests and does all that stuff for you, but there needs to be tests, right? It needs to be both giving your hardware design input stimuli, reading its output, and comparing against something. The thing we use in this course are these models. That's one methodology. Looking at things like print statements and waveforms, that's great for debugging, but that's not testing. Testing needs to be automated. Random can be great, but it's not perfect. So you may want to get some interesting corner cases and make sure you get those too. Another thing about random, if you have a very rarely occurring bug and you run random, and let's say it comes 100 times, And so it occurs once, and then you try to run it again. You run like 1,000 times, it doesn't happen again. And so there's two ways to handle it. Number one, if you log your test cases, you can at least rerun the same test case you know fails. Number two, there's something called seeding a random number generator. So when you seed a random number generator, it becomes less random because, of course, it follows according to the seed. That way, it's reproducible. So another option. We haven't covered assertions a whole bunch yet in this course. They are helpful. I recommend them, but they don't replace testing, right? You still need tests. Assertions are also great. They can catch a lot of issues, but they aren't a replacement for testing. They're complementary to testing. Um, and one thing pro tip I've found from many years of coding, both hardware and software, someday you're gonna have a really annoying bug. You're gonna spend days, maybe even weeks, hopefully not, finding it, and you finally find it. It's gonna be some super subtle thing, and you ask yourself, how could I change my code or my test benches so it's not so painful to debug this again? And oftentimes, one of the answers is, wow, there's some invariant about my design or my code that if this invariant's not true, it's going to be a bad time, right? And so that invariant, just put aside an assertion, right? That way, you can know early on where things go south. Usually, when you have those long debugging experiences, the problem is that the things went south or things went wrong far away from where the test failed. If the thing went wrong close to a test failed, usually you can find that pretty fast. But it's like the test fails, but then the issue is some very silent, subtle thing a long time before. It's hard to find that. Um, Searching help you catch those. Cool. Any last questions? Okay, well, that wraps that up.